at 9 a.m. So right now with Maziar Raissi, and then this will be followed by a regular presentation by Christopher Rakakis from MIT. And then at 11, we'll have Lulu, and 11:30, Kaleshu from Stanford. And at 12, Hossein Lu from MIT with reinforcement learning. So let's start with Maziar Raissi. So he's from UC Boulder, and he's going to talk about hidden physics model and how to use machine learning with nonlinear partial differential equations. So this will be a 1-hour invited talk. All right, thank you. So thank you, Maziar, for giving this this presentation under these unusual circumstances. And I guess you're showing us a boat of in the San Francisco Bay, maybe. I don't know if this is your Oracle team. All right, so if you want to start, thank you.
Okay, thank you, Eric. Do you hear me? Is it perfect?
Yeah, perfect. Yeah, great. Thank you.
Okay, thank you so much for the invite, and thank you for the nice introduction. I'm Maziar Raissi, Assistant Professor, Department of Applied Mathematics, University of Colorado, Boulder. And I work at the intersection of probabilistic machine learning, deep learning, and data-driven scientific computing. Everything started at Brown with a project that was to design supercavitating hydrofoils. These are hydrofoils that's gonna enable a marine vessel to go as fast as possible in water. Basically, these hydrofoils are gonna create vapor in water, and that vessel is basically flying in water, in the air. And everything ended with this work. So that one was external flows, this one is internal flows. This is the aneurysm of a real patient. The flow inside of it is simulated. And from that data, which is supposed to simulate the type of data that you get from MRI or CT scan, 4D MRI, basically time and space. And from that, you want to recover the quantitative flow properties, the things that matter the most. Like, what is the velocity field like? What is the pressure like? And what is the shear stress on the wall of that aneurysm? These are just more information to doctors to help them decide better. Okay, let's jump into it and go through the type of tools that we used. I'm not gonna be talking about these topics. I'm not gonna be talking about image classification, where you have images and you want to classify the type of the image, or you want to discover the category of your image. I'm not gonna be talking about language models or translations, and I'm not gonna be talking about generative adversarial neural networks. But what is the message? What is the take-home message from this slide? Is that the type of data that you have is gonna determine the type of model that we have to use. For instance, if you are dealing with images, probably a good model is a convolutional neural network. If you have language models, probably RNNs, and recently even convolutions or transformers can help you model your data. If you have a high dimensional distribution and you want to know, and you want to generate samples from that high dimensional distribution, then probably generative adversarial neural networks is the correct tool. In our case, where we had the design optimization of the supercavitating hydrofoil, we didn't have data. Basically, our data is going to be build the vessel, put it in water, and then collect data. And building the vessel is super expensive, and it's not feasible. What we did is we resorted back to simulations. So let's go back to simulated data. And let's model the supercavitating hydrofoil, and that's the 3D version of that. And let's do a 2D cross-section. The 2D cross-section, we parameterize it with splines. And at that time, we had 16 parameters, basically x11, x1, x14, x10, x13. These are the parameters. Given those parameters, we had a Reynolds average Navier-Stokes model. And it was actually a very good solver, and it would take 6 hours to give us data. That's the input data. The output data is the quantity of interest. In our case, it was lift over drag because we wanted to maximize lift over drag. And if you maximize it, you're coming up with the best design under some constraints, of course. This was the type of data that we had. Basically, the design is the input data, and the label for that data is the lift over drag. And to obtain these types of data, we had to run simulations. Change the input design, run your simulation, compute lift over drag. That's going to be your labeling data process. And each one of those data points takes 6 hours to be generated. So it's pretty expensive. But once you have the data, we want it to be data efficient. And to be data efficient, we started with Gaussian processes. I'm going to go through what is Gaussian processes very quick. For Gaussian processes, you have data. In our case, we have pairs of input-output data. The input data is xi, which is the shape of the hydrofoil, and yi is the label. In our case, it was lift over drag. And I corresponds then simulation, basically the first simulation, the second simulation up until the nth simulation. And if you have thousands of simulations, I denotes thousands of simulations. And we had a noise model because we were doing regression. And the regression, the noise model was normal with mean zero and standard deviation sigma squared. If you put everything in vector notation, you're going to get y, which is in Rn, and you have x, which is in which is a matrix, literally. It's in Rd, which d is the number of parameters that you have. You used it to parameterize your hydrofoil, and n is the number of data. That's the data. That's how we model the data. The question is, how do you model f, your function? We modeled f with a Gaussian process. That's our prior assumption. But what is a Gaussian process? A Gaussian process tells us that if you take any 2 points in your space, x and x prime, these are 2 points in our two designs, these two functions are correlated, they are normally distributed, they have a mean zero, and they have a covariance. kxx, kxx prime, kx prime, x prime. So rather than writing this notation all the time, that's going to be cumbersome. We are going to say f of x is a Gaussian process with mean zero and the covariance between x and x prime only. So Gaussian processes are just a shorthand notation for what you see below. Now everything boils down to the choice of the kernel, and the choice of the kernel corresponds to the basis function that you choose. In our case, one good example of a kernel could be the squared exponential covariance, which says that if you have 2 points, and if they are really far apart from each other, the corresponding values of those two functions, if you evaluate your functions there, they are going to be less correlated according to the distance because of the exponential and the negative sign. If a distance goes to infinity, these 2 points are not going to be correlated. So it has a local structure. It gives you a local structure for the type of functions that you're going to observe. And you have 2 hyperparameters, gamma and omega. The aim of the training is to come up with the best gamma and with the best omega, basically coming up with the best basis functions according to the data. Everything was normal. The data model was Gaussian. The prior is Gaussian. Therefore, your data is normally distributed with mean zero and a covariance matrix. So this covariance matrix results from evaluating your covariance matrix on your data points plus the noise model. And you can go ahead and write down your likelihood. Once you have your likelihood, you can go ahead and take the log of the likelihood and multiply it by a negative sign. Remove all of the constants that don't matter throughout your optimization. And you get an objective functions like this. The first term, y prime k inverse y, is trying to fit the data as best as possible. The log term, log determinant of the covariance, is gonna penalize the model, and it's trying to find the best model that fits the data, the simplest model. That's the aim of the training. We find our hyperparameters. Now we are going to do prediction. Somebody gives us a new design, X star. We don't want to run our simulation again. We want to use our surrogate. And the question is, what is the value of F at this new point, at this new design? What is your lift over drag? We are gonna write down the correlation between this new point and the data that we already had. And we're gonna condition on the data. Basically, we are conditioning f of x star on y, on our data. We are gonna get a mean and we are gonna get a covariance. This is the mean. And this is the variance. So everything is analytical. One thing to note about the mean is that it's just a linear combination of your kernel evaluated at your data. So these kernels are gonna act as a basis function. Okay. Let's try to visualize what the Gaussian process is doing. Let's collapse all of the input space, which in our case was 15-dimensional, and it could be higher dimensional, into the x-axis. And the y-axis is the lift over drag, in our case. If you run your simulations 20 times, you get 20 data points. The blue curve is the actual simulations that we don't have the luxury of seeing. So the blue curve we don't see. All we see are those data points, which sometimes are noisy. We fit a Gaussian process, we get a mean, and we get a standard variance, a standard deviation around the prediction. That's a typical prediction of a Gaussian process. But how can we use the uncertainty that we are getting out of a Gaussian process? You can start with two simulations. Basically, now you have two training data points. You can do your Gaussian process. You get a mean, you get a variance. Add to the mean a standard deviation of your predicted value. That's going to give you an acquisition function. In our case, it's on the plot on the right. It's called UCB. The red curve, the solid red curve, you can optimize. You can find its maximum. That maximum is going to tell us where to start simulation next.
sorry, just a quick question. So here you're assuming that there's no error in the data.
There could be error in the data. That's fine also. But usually,
is this what you're doing in the slide? No.
In the slide, no. There is no error in the data.
Right.
Because as you can see, the two training data are lying on top of the function. On top of the blue curve, but the blue curve we don't see. Now we are going to go ahead and find the next point using the acquisition function on the right. That's going to tell us where to simulate next. Which design should we try out next? We go ahead and try out that. And the objective here is to find the maximum lift over drag. So we want to find the maximum of the blue curve. But all we see are the training data. We go ahead and sample next. Here, we update our predictions, the mean and the variance, and we get an updated acquisition function. We are going to go ahead and sample next here. And already we are getting close to the maximum value. And we simulated only 1, 2, 3, and 4 times. But the algorithm is not happy because it thinks that there is uncertainty somewhere else. So it's going to go and explore there because the maximum could have been there. The function doesn't know. So it's going to go and sample there. The uncertainty is going to drop. It's going to explore again, explore, exploit, explore, exploit, explore, exploit, and it finds the maximum with minimal evaluation of the simulator. So we are not simulating that much. We are simulating only 13 times. So that was the idea behind how we optimized for the best design. But we had some more data, and we didn't want to throw them away. We had a potential flow solver. This one takes 6 minutes rather than 6 hours to give us the data. But these are low fidelity. By low fidelity, we mean these are less accurate, but you have many data points. You can evaluate your low fidelity model as much as you want, or as many times as you want. So here's an exercise. Rather than calling our high fidelity simulator, we are going to call and do simulations using the potential flow solver, the low fidelity one. We add 3 points, 3 low fidelity ones, and the function on the right updates the predictions. We add 3 more points. Now you have 6 low fidelity. The function on the right updates. And all of these are coming from writing the correlation between your high fidelity and a low fidelity. Basically, we are choosing a prior that is correlating these 2 functions together. Once you have that correlation, any data point that you get from the low fidelity model is going to help the high fidelity one. We use that to optimize our design. So we started with a design that was already optimized by genetic algorithms, and we were able to optimize it even further. So we not only did it for the supercavitating hydrofoils, we did it for the hull of the vessel. We use this methodology for every part to do design optimization on every part of that vessel. But so far, we were dealing with this physical system, but we were using no explicit physical knowledge. What we did was we collected data from a simulator of the physical world, and we applied a machine learning tool to it. Basically, we build a surrogate for our model. But the question is, can we encode our physics, our Navier-Stokes equations, inside the prior? Can we physics inform our Gaussian processes? That was the idea. And let's say this is your physics. Let's say this is a simplified version of the Navier-Stokes. That's the Berger's equation. And let's say this is our physics. We are going to go and discretize in time. So you have un minus un1, un minus 1 divided by delta t is the rest of your equation. We go ahead and approximate un by a Gaussian process. We take that Gaussian process and we push it through the differential equation, and we can find the correlation between yesterday and today. So what is, for instance, kn minus 1 and n? What is the correlation between yesterday and today? You can see that there is a one-to-one correspondence between your equation and the kernel that you get. You get k plus delta t, un minus 1, the derivative of k with respect to x, minus that parameter times kxx, where you are taking the derivative of your kernel twice. Any samples that you generate from this kernel is going to satisfy your equation and your discretization scheme. This is what we call a physics-informed prior. Basically, any samples that you generate from your prior is going to satisfy your equation. Okay, this is physics-informed, but how do we get the physics out? We get the physics out using data, training, and posterior. What is our data? The data could be data that you have at the initial time, at time 0. So we don't see the blue curve. We see only the data collected at time 0, and we get data on the boundaries. Let's say you have Dirichlet boundary condition. You can take that data, train the parameters of your kernel, which in our case is theta. These are the hyperparameters. Once you train it, you can condition on this data and do prediction. That's going to give you the prediction at time, I don't know, in this case it's 0.2, delta t ahead of ourselves. Now from time delta t, we want to predict 2 delta t. So we want to take another time step. But we don't have data at this point. The nice thing is that we have our posterior. From the posterior, we can generate artificial data. The mean is going to be your data points, and the variance is going to give you the uncertainty of those data points. Now that you have artificial data, you can do your training. You can find condition on that data, get the posterior, and keep predicting into the future. You can get a nice uncertainty band around the shock at time 1. So we are predicting into the future, given initial data points and some data on the boundary. And everything is data driven, and the data doesn't have to be on the boundary. There is a one-to-one correspondence between numerical Gaussian processes and Kalman filtering. But numerical Gaussian processes are for infinite dimensional objects. They are for functions. While Kalman filtering is for ODEs. So finite dimensional objects. The question is, how do you propagate the uncertainty? Why doesn't the uncertainty blow up? The idea is that the uncertainty is being propagated outside of the PDE. And this is how the uncertainty is being propagated. Sn minus 1, n minus 1 is the uncertainty of the artificial data points from the previous time step. So this is how the uncertainty is being propagated. That's why it doesn't blow up. So far, we were solving forward problems. Given our physics, we wanted to find a solver. We wanted to come up with new numerical schemes to solve that problem. And at the same time, we were getting something interesting. We were getting some uncertainty band around our predictions. And the way to interpret the uncertainty is how certain the model is about the solutions that it's giving us. So it's sort of an visual a posteriori error estimate on the predictions, on the solution. Now, can we use a similar methodology to solve inverse problems? What if you know your physics, but you know it up until some parameters? Let's say lambda 1, lambda 2, and lambda 3. This is the Koromatos-Sivashinsky equation. We go ahead and discretize over time. This is exactly the steps that we took for solving the forward problem. We go ahead and approximate u by a Gaussian process. We push it through the differential equation, and we get a kernel, which is physics informed. But something interesting happened. The parameters lambda 1, lambda 2, and lambda 3 of the differential equation turn into hyperparameters of the kernel kn-1n. Similarly, kn-1n-1. We are going to treat lambda 1, lambda 2, lambda 3 the same way that we treated theta, the hyperparameters of our Gaussian processes. This is nice because now you can use your likelihood to optimize over lambda 1, lambda 2, and lambda 3 without solving your equation forward. What does it mean? It means that if you have data, this is the data generated from Koromatos-Sivashinsky equation. And if you take 2 time steps, you collect data at 2 time steps. You have 2 snapshots of your solution, let's say at time 81.2 and 81.6. And your data could be scattered in space. They don't have to be on a grid. Then you can go ahead and optimize your likelihood and identify your PDE when you have clean data or when you have noise data. So something interesting is happening. This is Koromatos-Sivashinsky equation is a chaotic system. We are adding noise to it. We are depriving the method from enough data, and we are getting pretty good estimates for the parameters. Why is that happening? Why is this method data efficient? One reason is that Gaussian processes are data efficient by construction because of that log determinant term. The other is we are putting a lot of structure on our kernels, on the type of functions that we are going to see in the form of differential equations. We applied the same methodology on Navier-Stokes equation. And let's say you want to find the Reynolds number, and the Reynolds number corresponds to the shape of the object in front of us. Given 2 snapshots of the flow, you can find the Reynolds number as well as the advection term, advection coefficient. We tried to apply this methodology on experimental data, and the algorithm failed. And the reason is the equations matter. To do that experiment, the way the experiments were being set up is that it's an upside down. And it was soap film. When it is upside down, there is the effect of the gravity, and we didn't have the effect of the gravity inside our model. So the equations matter.
So I just have a quick question. So how do you optimize your parameter? Like what strategy, what optimization algorithm do you use to, or implementation, or how do you optimize the lambda parameters?
Oh, that one, you have a likelihood. It's the same methodology that you use for optimizing your the hyperparameters of the kernel of a regular Gaussian process. So you use
you have an explicit expression for that?
Yes, there is an explicit expression.
Oh, I see. Okay.
It's the one that I wrote on the first few slides.
I see, I see, I see.
Yeah, because everything is Gaussian, you have an explicit formula for that. So you have a data feed, that's y transpose your kernel inverse times y, that's where you have data,
right.
plus
with the log of k, yeah.
log of the determinant of k.
Right, okay, yeah, thanks.
That's what you use to optimize. That's your loss function. That's your objective function.
Okay, thanks, yeah.
Gaussian processes are beautiful, but they don't scale to big data exactly because you have to invert a matrix that's full and you have to find its determinant. So your matrix is a full, it's not sparse. It's a full matrix, and that one, you can invert it. The cost of doing that is order your data cubed. That's the cost of inverting those matrices. So the bigger
you have some fast, you have some fast algorithms in O of n to do that. But
yes, that's one way of doing it. The other way of doing it is, what if not all of your data matter? We are in the big data regime, in the big data world, but what if most of the data are redundant and noisy? This is an example of that happening. You have a lot of data for a simple function. Most of them are noisy data, and many of them are redundant. Can we summarize our big data set in a smaller one? Let's say in 8 data points in the case of this example. Think of it in terms of data reduction. It's equivalent to dimension reduction. So we are reducing the number of data. If you are able to reduce the number of data that you have to, let's say, 8 points, then you can apply a regular Gaussian process. But the question is, how do you get those 8 hypothetical data, or those few data points that you want? The idea is very simple. You take a mini batch of your data point, your huge data set, you take a mini batch, you condition on that mini batch, you get a posterior. From the posterior, you can generate samples. And we saw this happening when we were doing numerical Gaussian processes. We had artificial data. When we wanted to go from time delta t to 2 delta t, we had to generate artificial data. And we were using the posterior. So the idea is that your prior is going to give you a posterior. The posterior is going to be the prior for the next step. And you use this over and over again to update your data points. The red circles, they start from 0. All of them lie on the line of 0. And after a while, they get updated and they are right on the function that we are interested in. Where did we apply it? We applied it to satellite data. And these data are measuring the temperature of the ocean near Cape Cod. Cape Cod is near Boston. Some days are cloudy, so you have very few data points. I'm explaining the top row. Some days are cloudy, some days are sunny, you have a lot of data points, and some days are partly cloudy. From that, you can do your prediction. And whenever, by the way, whenever you have a spatial temporal time series, it's gonna be huge data points. It's going to be a huge data set. We were summarizing that data set in space and time with 10,000 points. So now our Gaussian processes have to deal with 10,000 points. That's going to give you a prediction, and that's going to give you the uncertainty map. And the uncertainty makes sense. Wherever you have data, the uncertainty is going down. So machine learning was helping us do our scientific computing. Now we help machine learning back with the idea of artificial data. Can we do similar things with neural networks? By the way, to get our kernels for Gaussian processes to physics inform them, we were taking derivatives of our kernels. And to do so, we were using symbolic differentiation. We were using something like Mathematica or Maple to give us the kernels. How about neural networks? Can we do a similar thing? Let's start with a brief discussion of how I think about neural networks for doing scientific computing. Data is the same as before. You have a data model. Now the question is, how do you model F? If you are doing scientific computing, you are going to say F is a linear combination of a bunch of basis functions, HL, plus a bias. So we write a linear combination of a bunch of bases. And if we are doing usual scientific computing, that would be game over at this point, because now we specify our HL, and let's say it could be our finite elements or finite difference or spectral elements, and we are happy. But what if you can learn your basis? You can say HL is a linear combination of a bunch of other basis functions that I don't know. But then that's going to be boring. That's why you need to put the nonlinearity. It could be tanh, it could be ReLU, it could be whatever that you want. But where do you get X? X comes in the first layer. For training, what do we use? Gaussian processes was all about the kernel of basically the covariance. Here, everything is about the mean. So if you write your likelihood, you get Y is normally distributed with mean, that's a neural network, and a variance. You take the log of the likelihood, log cancels out with the exponential, and that's the term that you get. Or if you expand it in terms of your data points, you get the usual mean squared error, assuming that your sigma you know. Once you train your parameters, which are the weights and biases of your neural network, you have your best basis function, literally. Now, the prediction, unlike Gaussian processes, for neural networks is very easy. You just put your X star inside your neural network and push it forward. That's going to give you the value. GPs versus neural networks, Gaussian processes are non-parametric. What do I mean? You have to carry your data with you all the time because you have to condition on them. That's why they are non-parametric. Neural networks are parametric. We are summarizing the data in our parameters. And the parameters are weights and biases. Gaussian processes are not scalable to big data sets. Neural networks are. Neural networks are scalable because you don't have to do your summation over all of your data points. You can do a mini batch of your data to get approximate gradients and do stochastic gradient descent. GPs are not scalable because you have to invert that matrix or find the determinant of that full matrix. Gaussian processes quantify the uncertainty. Neural networks don't. Gaussian processes balance the trade-off between data fit and model complexity. Neural networks don't. But these are the two extremes of the story. There are ways to scale Gaussian processes to big data And there are ways to encode uncertainty inside neural networks and try to regularize them. For instance, you can use dropout. But you have to work harder because these are against their nature. Neural networks is about the mean. Gaussian process is all about the covariance. Okay, now can we physics inform neural networks? If you go back to the previous slide, in that slide, we are using gradient descent to optimize. We have a loss function, we take the gradients of the loss function, and to compute the gradients of the loss function, we use automatic differentiation. But we are doing automatic differentiation with respect to the parameters of the model. You can do automatic differentiation with respect to time and space. And the idea is that the derivative of a neural network is a neural network. Let's say this is our physics. We are going to put a neural network, this is physics uninformed, on the solution. Basically, we are expanding our neural network in terms of a bunch of basis functions that we are learning. Now you can go ahead and take the derivative with respect to time, with respect to space, with respect to space twice, compute the residual of your differential equation, and return the residual. This is the meat of the code that you have to write for physics informing a neural network. Once you return f, how do you get the physics out? You do regression. You do regression on initial and boundary data, for instance, and you do regression on a bunch of scattered points in space and time on the residual. Basically, any samples that you're generating from the pair of your solution and the residual network, basically U and F, they share the same parameters. Any samples that you generate is going to satisfy the Berger's equation by construction. That's why it's physics informed. But we are not interested in every F. We are interested in a particular F, the F that is 0. That's why we do a regression on F and try to make it 0 on as many points as we want. Once you do that, you can solve Berger's equation given initial and boundary conditions. That's nice, but there is nothing special about it because we have better solvers. For instance, you can do finite differences to solve the same problem. Or you can do finite elements or spectral elements. You can do upwinding, downwinding, whatever. So there is nothing special as a forward solver with physics-informed neural networks, but things are interesting if you look at it from the machine learning perspective. You are training a neural network with only 100 data points. And most of those data points are just zeros. The only thing that matters is at the initial condition. That's the data efficiency that you get out of physics informing a neural network. And it's all because of the prior assumptions that you make, because of the physics. There is nothing special about the Schrödinger equation, but I'm including this slide to show the structure of the neural network. The neural network that goes from time and space to the real part and the imaginary part of the solution to the Schrödinger equation is a boring one, so there is nothing special. The gray box is very boring. It's fully connected. So it's not fancy, it's not convolution, it's not, I don't know, it's not a recurrent neural network, it's not LSTM, it's not a transformer model, it's a very simple model. But once you take the derivative with respect to time, things become interesting. Because you are taking that boring neural network, you are transposing it and you are taking the derivatives of the activation functions. If you have tan h, you get 1 minus tan h squared to compute the derivative with respect to time. And you're putting that neural network on top of the already neural network that you had. If you had 10 layers, after the derivative operation, you're gonna get a neural network that's 20 layers deep. If you take the derivative with respect to space twice, the depth of the neural network is gonna become 4D. So each time that you take a derivative, you're doubling the length of the neural network. And in the end, you compute your residuals. And to train it, you have mean squared errors at the initial condition, mean squared errors on the boundaries, mean squared error on the real part of your equation, and mean squared error on the imaginary part, and you can solve Schrodinger equation. So far, so good. But how do you compare it with the already existing landscape of solvers? For finite elements, finite volume, finite difference, you choose a basis function. That's your solution space. That's going to span your solution space. To span the solution space with a neural network, you're going to put a neural network there. With reduced order models, you choose your basis functions smartly based on your previous examples or based on previous times. How do you deal with the differential operators? If you have finite elements, finite volume, or finite difference, you discretize. Or you write your equations in their weak form and then discretize. So you're always discretizing your operator. With physics-informed neural networks, you're using automatic differentiation. And automatic differentiation, you are not sacrificing any accuracy. These are going to be machine precision operations. As for solver, if you have a finite element, finite volume, or finite difference, you use a linear solver, or you use a nonlinear solver, or you use iterative methods. Our solver for the physics-informed neural network is going to be gradient descent. That's training. And for evaluation, if you want to do nice plotting, and if you want to do post-processing, you do interpolation when you do finite elements, finite volume, or finite difference, or even reduced order models. For neural networks, you just do inference. You have your function that you can evaluate wherever you want. So this is how you can compare neural networks as solvers for PDEs with the existing landscape. But you get something more. With neural networks, you can go to high dimensions. If you have a high dimensional PDE, there is this theorem. The theorem is not mine, but it connects forward, backward stochastic differential equations and quasi-linear partial differential equations in high dimensions. You can go ahead and approximate your solution by a neural network. That's what we did. And we are going to use automatic differentiation to physics inform it. And then you can solve 100-dimensional Black-Scholes equations, or you can solve 100-dimensional Hamilton-Jacobi-Bellman. For the 100-dimensional Black-Scholes, you have 100 assets. You don't know, you know their price today. You don't know their price into the future. So that's going to be your forward dynamics, which you model it with mu and sigma. As for the backward dynamics, you want to know the price of an option on those assets. We know the price of an option in the future because the option is going to be either exercised or not exercised. But we are interested in the price of that option today. Not only today, but maybe delta t into after today, or the day after today, 2 days after today, 1 month after today. We want to know that price because we want to do trading. For the stochastic control, you usually come up with the Hamilton-Jacobi-Bellman equation. And again, you want to know the value. U here represents the value function. And the value function satisfies the Hamilton-Jacobi-Bellman equation. But why can we deal with high dimensional problems? Because with neural networks, your degree of freedom are your weights and biases. They have nothing to do with your space. With finite elements, for instance, or finite differences, you have to put a grid. In one dimensional, you can have a grid of 10 points. In 2 dimensions, you can have a grid of 10 to the power 2. In 3 dimensions, you can have a grid of 10 to the power 3. But then in 100 dimensions, you have a grid of 10 to the power 100. So that's not feasible. We are using the forward dynamics here to give us the data. And we have a good way of spanning the space, the 100-dimensional space, because of that theorem, because of the relationship between a forward, backward stochastic differential equation and a quasi-linear high-dimensional partial differential equation. Can you use physics-informed neural networks to learn parameters, to discover new dynamics? What if you want to know what is my Reynolds number? Let's say that's your exercise, and that's the Navier-Stokes equation. You can go ahead and say, I want to know my residuals, F, G, and H. You can approximate U, V, and the pressure by a neural network. You can take the derivative of those neural networks with respect to time and space and create F, G, and H. F, G, and H are neural networks of their own. They have a computational graph. Let's say this is your data. You collect data behind the cylinder, and you're collecting data at a scattered point in a space and time. And you're collecting it only on the velocity field, not on the pressure field. So absolutely no data on the pressure field. Because if you want to measure the pressure inside your flow, you're interfering with the dynamics of the flow. When we were writing that paper, to be honest, we wanted to know what is the Reynolds number. And the algorithm gave us that, even in the presence of noise. But it gave us something more. We had no data on the pressure, and the pressure popped out of probably nowhere. It's not nowhere, it's popping out of the continuity equation. And if you look at the scale, the predicted pressure has a scale from 0.9 up until 1.4. The exact pressure, or the one that we use for benchmarking, is from -0.5 up until 0.
Maziar, can I ask a question?
Yes.
This is Nat Trask from Sandia. So when you're modeling the pressure field, your choice of activation function actually defines what this basis is that you're working with. Can you describe, so this basis that you have here is able to resolve very small scale features of the pressure field around each eddy. Can you describe how you actually set that up? Like what the activation is, what the depth is, like those types of things?
So yes, for this one we have, it's a 10-layer deep neural network. We have, I guess, 256 neurons per layer. The activation function is a very good question. It's 10H, or it's Swish recently. And why is that? Why can't we just use ReLU? ReLU vanishes. If you want to take the derivative with respect to time once, that's okay. If you want to take the derivative with respect to space once, that's okay. You're gonna get some oscillations. But if you take the derivative with respect to space twice, and if you have the ReLU function as one of your activation functions somewhere in your layers, that's going to kill it. Basically, you're going to get a 0. So we didn't have the luxury of using ReLU. And as you know, ReLU is very important as an activation function for the success of many deep learning frameworks. We didn't have the luxury of using ReLU because we are taking derivatives with respect to space and time. And these have to be accurate. So yes, we didn't have data on the pressure, but the pressure is popping out of enforcing the continuity equation. This is a nice observation. We had absolutely no data on the pressure field, but we were getting something out of the algorithm. And by the way, the scales are off because the solution to Navier-Stokes equation, the incompressible one, is unique up until a constant. If you look at the equations, the derivative of the pressure shows up in your equation, not the pressure itself. So we had this idea that what if somebody has a stenosis, and the doctors are usually interested in knowing the pressure drop before and after the stenosis. Can we do the same thing? Can we inject particles in somebody's arteries, do the imaging, and do the prediction on the pressure field? That's going to give the doctor what he wants without doing any intrusive operations on the patient. The idea worked. We got some results. We can compare the left plot to the right plot, but it's not a publishable work because the idea is very stupid. You cannot inject particles in somebody's arteries because that person is gonna die. But we do imaging all the time. We do MRI and CT scan. People use dye, or people use the oxygen level of the blood flow to visualize what is inside, what is qualitatively happening inside our bodies. So we said, what if we have a passive scalar that is being advected and convected by the flow? And what if we have data on C, on the concentration of that passive scalar, which is a value from 0 to 1. Either the concentration exists or it doesn't exist. Either there is dye or there is no dye. So it's a value from 0 to 1. But it's a field. So you have data on the passive scalar, and you have the dynamics of the passive scalar. Let's say this is your exercise. Without any boundary conditions, you want to know what is the velocity and the pressure. If your Reynolds number is equal to the Peclet number, we tested, the algorithm worked. What if your Peclet number is less than the Reynolds number? We tested it, the algorithm worked. And what if it's bigger? The algorithm worked. So it was promising results at that time. And we were not using any boundary conditions. So we didn't have no slip boundary condition. So there is absolutely no boundary condition and no initial conditions being used here. The only data is the data on the concentration. So this led to this paper. Where we have data on the concentration. This is a 4D data, time and space. We have data only on this part of the neural network. So you have a neural network, most of it is unlabeled. Only this part of the neural network is labeled. So you are missing labels for U, V, W, and the pressure. But you have equations. You know that your concentration value is being advected by the flow, and you have your Navier-Stokes equations. That's going to be your hidden physics. You can do a simple regression on the concentration. That's going to help you reconstruct this flow, basically the plot on the right. And these equations are going to help you reconstruct the flow inside. The data that we are using is only collected inside the aneurysm. So that's the question. What is the boundary condition here? We are cutting the aneurysm sac from the entire arterial system. What is the proper pressure boundary condition? What is the proper initial condition? What is the proper boundary condition on the wall of that? It would be good to have a method that doesn't rely on boundary conditions or initial conditions. So apparently there is enough information in the concentration dynamics that's going to compensate for the lack of boundary conditions. That's going to help you reconstruct the flow. And in the paper, we are reporting the shear stress on the wall of the aneurysm. The other thing is that this is a data efficient algorithm. There is only one patient. We are not using simulated or real data from thousands of patients. This is the aneurysm of only one patient. So it's data efficient in that sense. Can we use the same framework for fluid structure interaction, multiphysics? The answer is yes. Can we couple ODEs and PDEs? So this is your particles, and you want to know the flow field, basically the Eulerian and Lagrangian frameworks. Can you do turbulence? Can you, given the probability distribution of your turbulent flow, can you recover the conditional distributions? Conditional diffusion, for instance. And the conditional objects are usually hard to find, hard to compute. Basically, there is this paper by Peyman, who is an expert in the field of turbulence. It took him 50 pages of rigorous mathematics to obtain the plot about exact D. Using this framework, we have data on the probability, and we want to get D. It's similar to the already mentioned framework that we had, and R is the residual network. Can you learn the dynamics from scratch? What if you don't know your ODE? Can you learn your ODE? What if this is x dot equal to f of x? That's your model. And you don't know your model. You don't know f. What is f? You can go ahead and discretize over time. You can approximate f by neural network, write down your loss function, and you can reconstruct your dynamics for the Lorentz system, for the Hopf bifurcation, for glycolytic oscillator, which is typical of biological systems, or Navier-Stokes equations on a low-dimensional manifold, on a 3-dimensional manifold. What if you have infinite dimensional objects? Now you know your physics. Basically, the framework is the same as before, but you don't know your physics. So it's physics informed, but you don't know your physics. The framework is the same as before. You collect data, for instance, out of the dynamics of the Berger's equation from time 0 up until 6.7. You learn the dynamics. You solve both of the dynamics of the exact system and the learned system. And you can do extrapolation, or you can change your initial conditions totally. We can do that for KDV, Koromatov-Sivashinsky, Berger's equation, And all of them are reported in that paper. And thank you for your attention.
All right. Okay. Yeah. Thank you. Thank you very much. Yeah. Great talk. So let's. Yeah. Thank you. So let's take some questions. So anybody from the audience? Otherwise, I'll.
Hi. I'm Kalai from Stanford, and I have a question about about the hidden physics model, and in this model, how do you assess the convergence of those parameters, those lambda and mu?
So the convergence is the convergence when you're optimizing.
Yes, like when do you, what's the stop criterion? Like,
for most of these methods, you usually use gradient descent.
yeah, yes.
And you let it train for a while, and then you report your results.
You mean when the loss is?
But you can have a stopping criterions if you like. For instance, once the change in the parameter, the relative change, is smaller than a threshold, you can stop your algorithm.
Okay, but because you use a loss function, you can scale every function in your loss function. Is so you set a deterministic threshold for the loss.
For the parameters, yes. If you want to get an accuracy of, I don't know,
okay,
some percent for, let's say, lambda 1 in this case.
Yes.
Your question is about this slide. When do you stop?
Yeah. Yes, that's right.
Yeah. So yes, when the change in lambda 1, the relative change in lambda 1 is less than a threshold.
Okay, I see. Yeah, thank you.
Yeah.
So let me ask you a question about can you go to the slide with the table that compares pin with ROM and define difference, right, this table. So how would you, so people, so you've shown the hidden physics and, many results, but you can do automatic differentiation with, let's say, the finite element and so on. So how would you characterize the problems for which pin would be the preferred approach versus, for example, a finite element scheme?
So yes, when it comes to forward methods, if you want to come up with a substitute for finite elements, basically as a forward solver, at this point in time, I wouldn't use physics-informed neural networks. Why is that? Because of the solver part, the linear, nonlinear, iterative schemes are really efficient. And they're gonna converge really fast. Gradient descent is not efficient. It's gonna take a lot of time for the training to end. But if your problem is high dimensional, then neural networks have an advantage. Or if you want to solve inverse problems. Why is that? Because for an inverse problem, you have to call your finite element solver multiple times. But the neural network one, you don't have to call it multiple times. It's just the parameters being optimized. Basically, for our inverse problem, similar to this case, lambda 1 and lambda 2 are just two other parameters on top of millions of parameters of your neural networks. So it's the same mean squared error that you're going to use to optimize this.
Presumably, if here you could use, you could do a automatic differentiation with the finite element scheme as well. So I would say that there is the issue of the boundary conditions, which is treated differently in both methods. Mm-hmm. But the inverse modeling itself presumably could be done with any number of schemes.
That's correct.
For example, for this lambda 1 and lambda 2, yeah.
Yes, so you are saying that here, that you're defining a neural network, you can define a finite element basis.
Right.
And the rest of it, you can keep it the same. And that's perfectly fine. This neural network here, you can put whatever that you want, whatever prior that you like. But I like neural networks because of the reason that they don't rely on the space. They are sort of meshless. Their degree of freedom is not tied to their space. It's just the layers, the weights and biases of the layers. So you don't have to create a grid.
Mm-hmm. Okay, great. Thank you. Any other questions? We need to move on to the next talk. I think we'll have maybe just a very short break, but any other questions? I guess not. Okay, all right. So let me thank our speaker, Maziar Raissi. Excellent talk, and thank you for giving this presentation